This is a video on set 21 question 2, which is the one about Kepler's second law. Perfect, that's convenient, so I'm going to go through it now. If we look at part A, it's calculate the rotational speed, which is also called the linear or tangential speed of a point on the surface of the Earth at the equator. So we can imagine the Earth is spinning around and we're just looking at a point on the very equator, on the very outside, which would be of course the fastest spinning part. Now, because we're looking at speed, this is basically a speed equals distance over time type of question. So we're using a formula that we are of course very familiar with. What we're going to do though is we're going to break it down using a formula from the formula sheet, which says V equals 2 pi r on t, where t is the period and of course 2 pi r is the distance travelled by a point on the equator. So, yeah, the circumference. So all we're going to do then is add in our values that we have, which is r for radius, which is given on the sheet, and for time, we're going to work out the time for 1 day, which isn't strictly 24 hours, it's going to be 23 hours, 56 minutes and 4 seconds, but if you worked with 24 hours, you get an answer that's probably close enough. So crunching those numbers gives us a velocity at a point on the equation, on the equator, of 465.24 meters per second. Looking now at part B, we're going to calculate the magnitude of the centripetal acceleration of a point at the surface of the Earth, again at the equator. So we're looking at basically what's the force associated with that rotational speed, or what's the acceleration associated with that speed. So how rapidly we're changing direction effectively. So we're going to use the formula straight off the formula sheet, which is A sub c, that's centripetal acceleration, equals v squared on r. Plug in the values, that's the velocity that we just calculated, 465 meters a second, and of course using the radius that we were already given, which was 6,380 kilometers, so 6,380 times 10 to the 3 meters. We plug those values in and that should give us 3.39 times 10 to the minus 2 meters per second. So of course in your calculator it should come out as 0.033926, but we can just use scientific notation to make it a little simpler. Moving on to part C, we're saying if the Earth was a perfect sphere, how would this affect the gravitational field of the Earth on the surface of the equator compared to the value at the poles? So what we're going to look at is the centripetal acceleration we've just calculated. So that's the acceleration of 3.39 times 10 to the minus 2. If we compare that to the acceleration due to gravity, which is 9.8, we know that we've got an acceleration due to gravity of 9.8 all over the Earth's surface. And so obviously at the poles, we'll just experience that because we're not really flying around as we are at the equator. If we're on the equator, we've got that little bit of centripetal acceleration acting in the opposite direction to gravity. So if we have a look at gravity at the equator, it's basically 9.8 minus that small centripetal acceleration, which gives us something that's about 9.77, which of course rounds up to 9.8. So we can see that our gravity on the equator is very, very slightly less than it would be at the poles. Hopefully that clears up that question. Thanks a lot.